Hello, and welcome to this third lecture in Unit 1 on linear algebra. Today we're going to be talking about special matrices and vectors. As always, this is presented by EDU Onyx. So let's go ahead and dive right in. To start, just a brief overview about what we're going to cover today. These matrices and vectors that we're going to talk about are used more commonly in machine learning because they are particularly useful. Oftentimes, they are useful because they are computationally efficient. As a result, using them in machine learning algorithms will speed up training, making them more efficient. When we are updating the parameters of a deep neural network, for example, it is computationally expensive. It takes a long time, so using some of these matrices and vectors can speed up that process. Furthermore, throughout the literature on machine learning, papers are going to use this terminology when they're talking about the structure of their networks or their algorithm in general. As a result, it's important that you have some understanding of each of these matrices and vectors so that you can understand what the author is discussing when they bring them up in their paper. So today specifically, we are going to be covering diagonal matrices, symmetric matrices, unit vectors, the process of normalization, which is how you obtain a unit vector, as well as orthogonal vectors. We will briefly mention orthogonal matrices as well at the very end. All right, so let's start with diagonal matrices. A matrix is diagonal if the following condition is met: di of j equals 0 when I is not equal to j. So we have a quick example of a diagonal matrix here down below. All this is a matrix where all the entries are 0 except along the main diagonal. So as you can see in this 3x3 matrix at the bottom, the index 0, 0 has a 1, index 1, 1 has a 2, and index 2, 2 has a 3. So when I is equal to j, we have a value. However, for all I is not equal to j, we fill in those entries with zeros. So this is diagonal matrix. Let's dive in a little bit deeper. Diagonal matrices are useful because multiplying by a diagonal matrix is computationally efficient. This is what I mentioned at the very start of this lecture in the overview. And let's go ahead and take a look at why that is. When you're multiplying a diagonal vector by another matrix, you only need to scale each element x of I by v of I. So here we have this diagonal v where the v is going to represent the elements of our matrix along the diagonal. So you have a vector v filling in the diagonal of a matrix, multiplying that by the matrix x. We only need to scale each element once. And so here we actually have some numerical examples. This is matrix multiplication. So if you move across the row on the first matrix, which is our diagonal matrix, you only have to perform one multiplication. You don't need those additional steps where you have to add in additional elements because they're all going to be equal to 0 except for 1. So you see on that first one, for example, we'd start on the first row. We'd have a 1 times 1 in the first column of our second matrix. However, as we move across the row in matrix 1 and down the column in matrix 2, all additional entries are going to be 0. Same thing for the second row. Everything's 0 except when we're multiplying the 2. And then everything is 0 except when we're multiplying the 3 on row 3. So theoretically, this matrix multiplication can be accomplished by only multiplying 3 numbers and then extrapolating those values to other parts of the matrix. So very computationally efficient. You can do this really quickly, and that's why they get used from time to time. So different authors or designers of machine learning algorithms will produce computationally efficient algorithms by restricting some of the matrices in their network to be diagonal. So you see this from time to time, and now you will understand why and how the authors are doing that. Also, diagonal matrices do not need to be square. So you can have a rectangular matrix. The main diagonal is going to cut across a rectangular matrix. And so you can end up with adding some additional elements or cropping some additional elements off of the end of your resultant matrix. However, just in general, You don't need to know too many specifics about that. All right, so that's diagonal matrices in a nutshell. Let's go ahead and move on to symmetric matrices. Just as the word implies, these are symmetrical, and they're symmetrical across the main diagonal. As a result of that, a symmetric matrix is going to be equal to its own transpose. Since intuitively, the transpose of a matrix is simply flipping it over the main diagonal, it makes sense that a symmetric matrix across that same diagonal is going to be equal to its own transpose. So here we have an example of that. If we have the following matrix, we have 1, 2, 3 in the first row. We also have 1, 2, 3 in the first column. You can see as we flip this across the main diagonal, we're going to get the same matrix back. So this is a symmetric matrix because it's equal to its own transpose. And symmetric matrices often arise when the entries are generated by some function of two arguments that does not depend on the order of arguments. So for example, if our matrix A here is a matrix of distance measurements with AI of j giving the distance from point I to point j, then AI of j is going to be exactly equal to AJ of I. So flipping the rows of columns isn't going to matter. And this is because distance functions are symmetric. So a lot of the times when you see Euclidean distance come up in machine learning, you are going to get symmetrical matrices as a result of the use of that Euclidean distance. So these come up from time to time because of symmetrical functions. All right, let's move on to the unit vector. A unit vector is a vector with the unit norm equal to 1. So we talked about norms in the last lecture. Here we're using the L2 norm or the Euclidean norm. And whenever this Euclidean norm is equal to 1, we have a unit vector. So these unit vectors can be obtained by normalizing any vector. So let's talk a little bit about that process. Normalization is the process of dividing a vector by its magnitude, which produces a unit vector. So we mentioned in the previous lecture that the norm of a vector or matrix, the L2 norm specifically, is going to be the magnitude of that vector. So when we divide by that magnitude, we are going to produce a unit vector. So let's dive a little bit deeper into an actual example. If we have the vector here, x is a length 4 vector with just all ones. Down below in this step, you see we have the fraction. We have that vector x divided by its L2 norm. So we have L2 here filling in the 2 for the p in the equations we talked about previously. We're going to have 1 squared. Since each element is 1, we're going to have that 4 times. Taking the square root of that, we're actually going to get back 2. So dividing each element by 2, you are going to now have 1/2 for all of the entries in this vector. And actually, if you went back and you took the L2 norm of this resultant vector, you'd see that it is indeed equal to 1. So this is a unit vector. It has been normalized to where the magnitude of the vector is equal to 1. So normalization is a common pre-processing step and has been shown to dramatically improve the performance of machine learning algorithms in a lot of cases. So normalization is very common, and when we're doing that process, we're typically going to use a Euclidean norm or the L2 norm for the magnitude of the vector because it's going to produce a unit vector for us. So everything is going to be normalized between 0 and 1 in this scenario. So that is vector normalization. It comes up all the time in pre-processing, as we mentioned. Occasionally, though, you'll actually see normalizations of the weights and the parameters in a machine learning network as well. Specifically, deep neural networks, you may see normalization between the layers of the particular network. So that comes up, and it's important to understand what that normalization process is actually accomplishing. So, as I mentioned, the vector here has a magnitude of 1, which makes it a unit vector. All right, let's touch on orthogonality. So a vector x and a vector y are orthogonal to each other if the transpose of x times y, we have matrix multiplication here, or just simple vector multiplication in this case, is equal to 0. So intuitively, this is going to occur if these two vectors are at a 90-degree angle to each other. So since we're dealing with vectors here, we can assume that we're talking about a two-dimensional space, and the inner product in that two-dimensional space is going to have this 90-degree angle. So also, we can extend upon that and say if two vectors are orthogonal and they're also unit vectors, they are called orthonormal. So this is just a combination of normalization as well as orthogonality, and we can get orthonormal as a result. So here's an example of orthonormal vectors. We have two vectors here, 1, 1 and 1, -1, and they're at a perfect 90-degree angle to each other in this two-dimensional space, and they're also normalized as well. Oh, actually, this is not an example of orthonormal because the magnitude of these vectors is actually going to be slightly larger than 1, so I apologize. This is not orthonormal, this is simply orthogonal vectors. To get orthonormality, we would have to calculate the unit vector for each of these. So we have, for example, the 1, 1. The L2 norm of that would be 1 squared plus 1 squared, so the square root of 2. If we normalize this to where each element was 1 divided by the square root of 2, we would then have orthonormal vectors. So this concept can also be extended to matrices. However, if we say we have orthogonal matrices or an orthogonal matrix, we are going to have a square matrix whose rows are mutually orthonormal and whose columns are mutually orthonormal as well. So the rows and columns are going to be orthonormal to each other, and as a result, we get out an orthogonal matrix. But that isn't used quite as commonly, so simply understanding that orthogonality in this case is going to be the multiplication of the transpose of one vector times another vector is equal to 0. If you've done some multivariate calculus or linear algebra in the past, you've heard of this as the dot product. So the dot product of these two vectors is going to be equal to 0 as well. So that is orthogonality in a nutshell. And again, these concepts could be expanded upon for many hours. However, we're just touching on them briefly so that when they arise in different machine learning papers, you have a simple understanding of the concepts presented in. Again, this is simply an introduction to the essential maths for artificial intelligence, so we're not going to spend too much time on each one of these concepts individually. We're more concerned with the bigger picture and the overall implementation of the math in these machine learning algorithms. Okay, so that's going to bring us to the end of this lecture. In the next video, we're going to touch on eigenvalues and eigenvectors for the purpose of eigendecomposition. You may have heard of this before in the context of principal component analysis. So that'll be really interesting, and that is actually going to be much more complex than some of the linear algebra that we've touched on so far, so we're going to have to go a little bit deeper than we have up to this point. So stay tuned. Thank you very much for listening.